A hearty welcome to one and all on a new lecture as part of the lecture series conducted by Postgraduate Department of Mathematics, SVR NSS College, Vazhoor. I congratulate the organizers for conducting this wonderful lecture series, which I am sure is benefited to whole students community as well as the mathematics enthusiast. I also thank the organizers for inviting me on this lecture and giving me an opportunity to deliver a lecture on one of the most fascinating topics I have ever come across my mathematics career, which is infinity. So my lecture is titled Infinity, a Mathematician's Lament. Myself, Liju Alex, Assistant Professor, Department of Mathematics, Bishop Chulaparambil Memorial College, Kottayam. Infinity, as the name suggests, is something which beyond our comprehension. It is something which was defined and discussed by many scientific experts in various fields, but many of them haven't had much success in defining or properly understanding this concept in general. As for the most difficult concepts all across the universe, our subject mathematics separates itself from all other science with this simple fact that we can actually define, understand, improve, and give a concrete understanding and a concrete basis to any difficult concept which anyone can comprehend. For other scientific fields, this concept of infinity might be a really difficult one. But to mathematicians, it is really one among other concepts which they have properly defined, understood, and developed. So, in this lecture, we deal with an undergraduate level lecture, which will discuss about the concept of infinity in general and the following matters. So, the first thing which we are going to discuss is the historical aspects regarding the concept infinity. And the next one is the one-to-one correspondence and comparison of cardinalities between different types of sets, and the famous Hilbert Hotel problem, which was proposed by David Hilbert, and different classes of infinity, if such a thing is possible. And the last part, the continuum hypothesis. So, this will be the order of my lecture. So, without wasting much time, let's move on to the main contents of our lecture. So, infinity, through long years of mankind, have been always haunted us. From the early part of scientific developments, we have used the concept of infinity by various means. Even though it has been properly used by various scientists, none of them properly understood, developed, and defined this concept. So, in the first aspect, I will divulge into some concepts or some theoretical background which were used but not properly defined the concept of infinity. The first one was Euclid's infinitude of prime numbers. We all know that the prime numbers in size, the total number of prime numbers is actually infinite. Euclid also understood this fact and stated that prime numbers are more than any assigned magnitude of prime numbers, meaning there are infinite number of prime numbers. So even though he understood that there are a lot of prime numbers which cannot be restricted onto a definite number, he didn't actually used the concept of infinity to examine or understand this thing. What he has done was he understood that if you are given finitely many prime numbers, you can actually construct a new prime number from that simple fact. So if you continue like that, you can actually develop sufficiently many prime numbers which exceeded any particular limit. So which means that there are infinitely many prime numbers. So this was one of the first concept which used the concept of infinity in its core but not actually define something like that. So in this, it is trivially establishes that this statement there are infinitely many prime numbers but does not give much insights to the concept of infinity itself. So this was one of the first concept which used the concept of infinity. Later, Newton used infinitely small number to define the derivative of a function, the continuity, and Cauchy used it to define the infinite sum. So all of these mathematicians through the centuries have used the concept of infinity in various forms without actually defining or without actually having a much better understanding of the concept itself. So through the ages, infinitely or infinite has been properly used by various mathematicians. The prime number theorem or the infinitude of prime numbers by Euclid is one such example. And another one is a famous paradox by Zeno of Ilia regarding Achilles and tortoise. Achilles is a Greek legend. He is considered to be the most physically attributed man lived across the globe. So, Zeno, in his paradox, considered the following aspects. So, what Zeno considered was the famous physically attributed man Achilles and the least speedy animal across the globe, a tortoise, both of them races together. Since we already know that Achilles will be far more faster than the tortoise, we will give a head start to tortoise because to make the event more competitive. So what we are going to give is we are giving a head start of let's say 100 meters. So the tortoise starts 100 meters far away from the Achilles. So Achilles has to travel these 100 meters or Achilles is behind tortoise by 100 meters or some other distance. And Zeno's argument was quite interesting. He argued that when the race starts, Achilles, which starts from the original point, let's say this point, and tortoise starts from this point. Okay. And when Achilles reaches from this point to this point, the tortoise will move slightly forward or the tortoise will travel some distance. And when Achilles moves from this point to this point, again the tortoise will travel some other distance. So the tortoise will be somewhat ahead of Achilles. And again, if the Achilles travels from this point to this point, again the tortoise will within that time will travel some more distance. And again the tortoise will be ahead of Achilles. So if we continue like this, we can always assume that Achilles, he is even very much faster than the tortoise, is always behind the tortoise. So in this concept, so by this logical argument, Zeno argued that Achilles, who is very much faster compared to the tortoise, will never cross the tortoise and go ahead of the tortoise. Even though for a layman this looks very foolish, because within a definite amount of time Achilles will always travel past the tortoise. But by this argument, which says that when Achilles is in point A, the tortoise is in point B, the race starts. When Achilles reaches from point A to point B, the tortoise will be ahead on some distance, which is, let's say, point C. When Achilles reaches point C, the tortoise will be ahead in some distance, point D, within that permitted time. When Achilles reaches point D, the tortoise will be ahead by some distance, point E. So by continuing this logic, Achilles will always be behind the tortoise. So this was the idea. So if you continue this process infinitely many times by Zeno's argument, in between any 2 points there are infinitely many points. So we can actually continue this argument for infinitely many times. So by continuing this logic, the Achilles, who is a far superior athlete than the tortoise, will not get past the tortoise. That's the argument. So why he made such an argument? Because he hadn't had much insight regarding the concept of infinity. So let's look into some mathematical aspect of this. Let's say Achilles is running at 10 meters per second and the tortoise is walking 0.1 meter per second. So within 1 second, Achilles can travel 10 meters, and within 1 second, the tortoise can travel 0.1 meter. And assume that the tortoise is 100 meter ahead of Achilles. So this distance is actually 100 meter. The tortoise starts 100 meter ahead of Achilles. So by this argument, using simple physics, in order to travel 100 meters, Achilles needs 10 seconds. Okay, by those 10 seconds, the tortoise will travel 10 times 0.1 distance. That is 0.1 distance. So after 10 seconds, Achilles will reach here. The tortoise will be 0.1 meter ahead of Achilles. And in order for Achilles to reach the distance 0.1, he needs 0.1 seconds. And within that permitted time, the tortoise will travel 0.1 times 0.1, which is 0.001 distance. And if you continue like this, the time which will allow Achilles and tortoise to travel will be the first 100 meters, Achilles took 10 seconds. The next is 0.1 seconds, which he needed to travel point C. and next point D, he needed 0.001 seconds and continue like this. So which is actually 10 plus zero point 0.1 plus 0.001 plus 0.0001 plus etc. So the total time taken by Achilles will be 10 plus zero point 0.1 plus 0.001 plus 0.00001 plus etc. Which is clearly an infinite sum. So Zeno's concept was, since we are summing actually infinitely many numbers, it is not actually possible to have a finite sum. So this was the main problem which was occurred to Zeno. But which was later a famous mathematician Cauchy in 1821 proved that the sum of geometric series, here A is 10 and R is 0.01. So this is a geometric series with first term 10 and common ratio 0.01. Its sum is actually A divided by 1 minus R, which is 10 divided by 1 minus 0.01. So this is the answer. 10 by 0.99 will be the answer. So clearly, which is a finite number. So within the permitted time, within a finite number of time, or within 11 seconds, Achilles actually traveled past the tortoise. So due to the lack of knowledge about infinity and infinite sum, that problem was continued to be a paradox for over 200 years. So this was the early aspects of or early discussions regarding the concept of infinity. Now, in order to understand the concept of infinity, we need some set theoretical knowledge or some basic terminology to be moved forward. The first concept is a set. A set is a well-defined collection of objects. So it is a collection of objects which we can actually contribute, which is a well-defined, which means every element, if you take an arbitrary element, we should be able to say that whether that element should be in the set or not in the set. Some examples are set 1, 2, 3, 4, set ABC, set of all natural numbers. So these are the examples of sets. And similarly, we can actually define a subset. A set capital A is said to be a subset of capital B if every element of A is in B. So set 1, 2 is actually a subset of set 1, 2, 3, 4. Set AB is actually a subset of set ABC, and so on. So these are the basic terminologies which we already know about set. Now move on to injection, surjection, bijection. So surjection means onto functions. So which means that corresponding to every point in the domain or corresponding to every point in the codomain, there should exist an image. So every point in Y where the function is defined from x to y should be an image of some point in capital X. So every y should be of the form f of x where x belongs to capital X. So this type of functions is actually surjections. And injections, this is not actually a surjection clearly because this element is not the image of any other element. So defining injection, so injection means corresponding to every element x, there exists a unique element y such that f of x is equal to y. And if you take another element and you consider its image, the images should be different as far as the element should be different. So this is actually an injection or one-one functions. If a function is actually both injection and surjection, which is called bijection. So this is what we already know. Now moving on to defining or developing the concept of infinity or understanding the concept of infinity. So for that we need what is actually a finite set. We are actually using set terminology, set theoretical ideas to actually understand this concept. So a finite set is a set with a definite number of elements. So you can actually say how many elements are in a set. If that's a natural number, then you should be able to say that that set is finite. A set which is not finite is actually called infinite set. So that's the definition of finite and infinite set. So if you consider this three apples, this is actually a finite set because the number of elements is actually 3. So in order to establish whether or not a set is finite or actually finding the size of a set, we actually need to count the elements of the set. In this case, we counted 1, 2, 3 apples. So we need to count the number of elements in order to establish whether or not a set is finite or not. So if at all the counting is terminated or the counting is ended, then we say that the set is actually finite. If it is not ending, then the set is called infinite set. So that's the idea. So can you use this same argument of counting to establish an infinite set? That's our question. Which is not possible because of the simple fact is that within a definite period of time, you can only count up to definite number of elements. Within say 100 years, which is your lifespan, you can actually count a definite number, up to a definite number. So beyond that, if our set consists of a number of elements which beyond that, we cannot say that that is an infinite set because after that also, if the set ended, then also the set has only finite number of elements. So this idea of counting is not at all useful or feasible to understand the case of infinite set. So what we need? So what we need is the concept called one-to-one correspondence, which was, I think, one of the first mathematical concepts which was used by mankind. So in the earlier cases, man only know the numbers 1 and 2. So if he has 100 sheep, what does he say? He cannot count up to 100 numbers. So what he is going to do is he put a rock corresponding to each sheep. So if there is 100 rocks, which means that he has 100 rocks. So whenever the sheep goes outside, he places the sheep on the right hand side, let's say. Whenever the sheep is inside, he places the rock on the left hand side, let's say. So if at all, after the evening, if at all all the rocks are in the left hand side, he can certainly understand that all the sheep are inside. So what he does is, he did not count actually the numbers. He assigned everything corresponding to a rock. Or in other words, counting can be done using another perspective as well. So 3 apples without counting, also we can understand this is actually 3 apples, or this is actually a finite set by defining 3 numbers to these 3 apples. So actually what we are doing is, we are assigning number 1 to the first apple, number 2 to the second apple, number 3 to the third apple. So this is actually a one-to-one correspondence or a 1-1-on-2 function. So actually you are defining corresponding to 1, there exists a unique apple. Corresponding to 2, there exists a unique apple. Corresponding to 3, there exists a unique apple. So you are actually defining a one-to-one correspondence between the set of apples and the set 1, 2, 3. So if at all such a one-to-one correspondence exists, then also you can say that the 2 sets have the same number of elements. So that's what the one-to-one correspondence or equivalence means. The 2 sets are said to be equivalent if they have the same cardinality. Cardinality means the number of elements of the set. Now the question is, For a finite set, you can actually count up to a finite number and establish that whether or not two sets have the same cardinality. If two sets have the 10 number of elements, they have the same cardinality. If two sets having 15 number of elements, they have the same cardinality. But you cannot actually count the infinite set. So you cannot actually count the infinite set. So which means that you cannot say that using these conditions, you cannot say that two infinite sets have the same cardinality. So how does we say that? So I already told you, counting is another way of defining a one-to-one function. So here, this is a bijection, which means that x and y have the same number of elements. Here x and y have different number of elements. So the function is only injection, not a bijection. Here also x and y have different number of elements. So the function is only a surjection, not an injection. So if at all two sets have the same number of elements, which means that there exists a bijection from the first set onto another set. So which means that the cardinality or the number of elements or counting process is equivalent to defining a one-to-one function or a bijection from a set onto another set. So that's the way we proceed in order to establish whether or not two infinite sets have the same cardinality or the same size. So two sets M and N are equivalent if there exists a bijection from M to N. So in this case, we are not actually counting the total number of elements. We are assigning corresponding to each element, does there exist a unique element, and if that process is possible to define, then we say that the two sets have the same cardinality. We are not actually counting 1, 2, 3, 4, etc. So the counting process is one other way of defining a one-to-one correspondence between two sets. So that's the idea. So counting is essentially a one-to-one correspondence or a bijection between two sets. And using this concept, we can actually define what is a finite set. So in the case of three apples, we have defined a bijection from set 1, 2, 3 onto the three apples. So a set A is said to be a finite set if there exists a bijection from set 1, 2, 3, etc. up to n onto A for some n. So if a set has 5 number of elements, then there should exist a bijection from set 1, 2, 3, 4, 5 onto that set. If a set has 100 elements, then there should exist a bijection from 1, 2, 3, etc. up to 100 to that set. So if at all, for a particular natural number n, there exists a bijection from 1, 2, 3, etc. n to that set capital A, then only we can say that the set is finite. So we are not actually counting the numbers. We are actually assigning a function. We are trying to define a function from this set onto capital A. If that is possible, the set is called a finite set. Now, what about infinite set? How, using this regard, how can you define the concept of infinity or infinite set? As we already know that set of all natural numbers can be counted, and also the counting process cannot terminate. So which means that this has infinitely many elements, clearly. Or it does not have a bijection from set 1, 2, 3, etc. particular n onto set of all natural numbers for a particular n. So which clearly establishes the fact that set of all natural numbers is infinite. Now consider set of all even numbers. I already told you the two sets have the same cardinality if there exists a bijection between those two sets. Now from the set of all natural numbers onto set of all even numbers, we can define a bijection which maps 1 onto 2, 2 onto 4, 3 onto 6, 4 onto 8, 5 onto 10, etc. in general n onto 2n. So this is actually a bijection clearly. Corresponding to every natural number, there exists an even number which is 2n. So from this regard, even though set of all even numbers is a proper subset of set of all natural numbers, which means that natural numbers contains more elements than set of all even numbers, but using the concept of cardinality, they must have the same number of elements. So even though set of all even numbers is a proper subset of set of all natural numbers, both of them must have the same cardinality. So that's the first idea regarding the infinite set. Similar assumption can be made in the case of Z as well, set of all integers. So from set of all natural numbers to set of all integers, we can define a function which assigns 1 onto 0, 2 onto 1, 3 onto minus 1, 4 onto 2, 5 onto minus 2, etc. That is, every even number onto its half, every odd number onto the corresponding negative numbers. So we can define such a function. Clearly from this, if we continue like this, it is like sweeping. Take the first integer, then from the right hand side take the next positive integer and the corresponding negative integer. Next to positive integer, corresponding negative integer. Next to positive integer, corresponding negative integer. So if you assign something like this, clearly you can understand that there exists a bijection from n to z. So the cardinality of n and the cardinality of z is actually same, even though set of all natural numbers is a proper subset of z. So that's the prime characterization of an infinite set. So in the case of infinite set, a set can be said to be infinite if there exists a one-to-one correspondence from a set onto at least one of its proper subsets. So a set is called infinite set if there exists a bijection from that set onto one of its proper subsets. If that is possible, then the set is called infinite set. So this is the prime characterization of an infinite set. So we have actually defined an infinite set as well. So using one-to-one correspondence, we have successfully defined finite and infinite set. The first definition, even though it looks pretty, it has some lacks. It lacks some conceptual background. Now these definitions are definite, it has mathematical background, and it is pretty clear. So we have successfully defined or understood a finite set and infinite set using a bijection or a one-to-one correspondence. Now, let's say two sets, A and B. If there exists a bijection from A to B, we say that A and B has the same cardinality. Now, what about comparing the cardinality? What about cardinality of A less than cardinality of B? Let's look into our surjection, bijection, etc. So, if there exists a surjection, clearly corresponding to every y, there should exist at least one element in x. So, which means that from this definition itself, the number of elements of y should be less than the number of elements of x. Because corresponding to every element, we must have at least one element in x. So, two elements can also map onto some element in y. So if there exists a surjection from x to y, clearly the cardinality or the number of elements of y should be strictly less than or equal to the number of elements in x. And also in the case of injection, corresponding to every element in x, there exists a unique element in y, which does not mean that every element in y is actually an image. So which means that corresponding to every element in x, there should exist at least that much element in y. So which means that if there exists an injection from x to y, the cardinality of x should be less than or equal to the cardinality of y. So this is how we compare the cardinality of two different sets using one-to-one correspondence. So if at all there exists a surjection from A to B, then we say that the cardinality of B is actually less than the cardinality of A. And if there exists an injection from set A to B, then we say that the cardinality of A is actually less than the cardinality of B. So not only the equality of two sets or the sizes of two sets can be established using one-to-one correspondence, the comparison or the sizes comparison or less than part or greater than size of two sets can also be established using this one-to-one correspondence. So this is not at all a concept which is restricted to equality of sets. Comparing the sizes of two sets can also be done using this one-to-one correspondence. Now let's look into the concept of infinity in detail. So we have defined or understood that set of all natural numbers is actually an infinite. Then the size of the set of all natural numbers or the number of elements of the set of all natural numbers or the cardinality of set of all natural numbers is an infinity. That infinity is called Aleph naught. Now, does this Aleph naught has some properties? This Aleph naught is called actually a transfinite number. A transfinite number is a number which is not finite. So, actually, the class of infinities can be collectively called a transfinite numbers. So, Aleph naught, which is the cardinality or the number of elements of the set of all natural numbers, is a transfinite number. Now, does this transfinite number have some sort of properties like the usual numbers? So, which is what we are going to discuss. In order to establish or understand that, we need a classic paradox which was proposed by Hilbert. The paradox is called Hilbert's hotel problem. So, consider a hotel which consists of infinite number of rooms. The rooms are assigned 1, 2, 3, 4, 5, 6, etc. So, we have a hotel of infinite number of rooms. Now, each room is being occupied by guests. So, every room there exists a guest. Now, a new guest arrives. Assume that a new guest arrives. So, the question is, can the hotel manager accommodate the new guest? We have the condition that we have as many rooms as the natural numbers because we have infinitely many rooms and each room is assigned by a natural number. So we have as many rooms as the natural numbers and each room is being occupied. So what about a new guest? Since this is actually the set of all rooms or the number of rooms is actually a transfinite number, we can actually do that. In the case of finite, a hotel with the finitely many rooms, we cannot do that. So what we are going to do is, we are informing the guest in the nth room that you should be moving on to the n plus 1th room, which means that the guest in the first room is moved on to the second room, and the guest in the second room is moved on to the third room, and the guest in the third room is moved on to the fourth and fifth and etc. So if you proceed like this, clearly the first room becomes vacant. Okay, so you can continue like this. So which means that you can accommodate the new guest onto the first room. So our total number of rooms in the hotel was Aleph naught. We have one more guest. Corresponding to that also, we have one more room. So in general, Aleph naught plus 1 is actually equal to Aleph naught. So what about 10 guests? Can you accommodate 10 guests as well? Which is also possible. Using the simple logic is that you are informing the guest in the nth room to move on to the n plus 1th room. So which means that the guest in the first room is moved on to the 11th room, the guest in the second room is moved on to the 12th room, the guest in the third room is moved on to the 13th room, etc. So which means that the first 10 rooms becomes vacant, so you can assign the new 10 guests the first 10 rooms. So also If we add 10 more people onto the already existing set of cardinalities, the cardinalities won't change. So this can be done in the case of any finitely many cases. So if you have the cardinality of set of all natural numbers or a type of infinity which is called Aleph naught, if you add finitely many numbers or finitely many terms to that, the cardinality does not actually changes. So in other words, you have the set of all natural numbers, you are taking finally, you are adding finally many terms onto the set of all natural numbers. It does not actually change the total number or total size of the natural numbers. So this is true for any finitely many cases. So if you are finitely many guesses has been arrived, instead of 10 you have 100, 1000 or any other number, you can actually assign using this assignment, moving the guest in the nth room onto the n plus kth room. So that's the idea. So what about infinite number of guests? So in a bus which can accommodate an infinite number of people, so in this hotel, every room is being occupied and a bus containing infinite number of guests has been come. How can we accommodate this? So if it was finitely many cases, we know that we can actually manage this. Infinitely many cases also we can actually manage this. So what we are going to do is, we are actually assigning or informing that every guest in the nth room should be moved on to the 2nth room, or the first guest in the first room should be moved on to the second room. The guest in the second room should be moved on to the fourth room. The guest in the third room should move on to the sixth room, and so on. So if you continue like this, the odd numbered rooms, that is room number 1, room number 3, room number 5, room number 7, etc., is being vacant. Now we have only infinite number of people and each of them should be assigned in the odd numbered rooms. So what we have done is, we have infinite number of elements, we have added an infinite set onto that, still the corresponding cardinality does not changes. So instead of adding finitely many terms, if you are adding actually an infinite number of terms with a definite order, still the cardinality does not actually changes. So these are the classic properties of the transfinite number, or one class of infinity called Aleph naught. Now let's stretch a little bit more. How about infinite guests coming by infinite number of guests? In the first case, we have only finitely many guests. The second case, there are infinitely many guests coming by only one room, one bus. Now in this case, we have infinitely many buses and each of the bus consists of infinitely many guests. So can you accommodate that? This can also be done in this hotel because it's an imaginary hotel and our manager is actually a brilliant mathematician. So what we are going to do is, we are assigning the room numbers in this way. The first row consists of only 1, the second row consists of 2 and 3, the third row consists of 4, 5, 6, fourth row consists of 7, 8, 9, 10, which means in the first row only 1 element, second row 2 elements, third row 3 elements, fourth row 4th element, fifth row 5 elements, sixth row 6 elements, and so on. If you continue like this, you can actually get a pyramid, an infinite pyramid. Now what we are going to do is, consider this diagonal. This diagonal, if you stretch forward, consists of infinitely many elements. So what we are going to do is, we are telling that the already existing guests in the rooms to move on to these room numbers. That is, the guest in the first room should be staying on the first room, the guest in the second room should be moved on to the third room, and the guest in the third room should be moved on to the sixth room, and the guest in the fourth room should be moved on to the 10th room, and so on. Now, all other rooms becomes vacant. Now take the first best, guest in the first best. So the first member in the first best has been assigned room number 2, and the second guest assigned room number 5, third guest room number 9, fourth guest room number 14, fifth guest room number 20, and so on. So if you continue like this diagonal, it consists of infinitely many elements. So all the guests in the first best has been assigned. Now moved on to the second best. So the first guest in the second best has been assigned room number 4. The second guest assigned room number 8. The third guest assigned room number 13, and so on. So if you continue like this, we have infinitely many elements. So every guest in the third best also been assigned. Similarly, the fourth guest can also be assigned this way, this diagonal, 7, 12, 18, and so on. The fifth guest can be assigned in this way, 11, 17, etc. Since these diagonals is never ending, corresponding to each best, we must have a diagonal consisting of infinitely many elements. So every new guest which has been coming by this way has also been assigned. And this is one way of doing this problem. Another way of doing this problem is using the simple fact is we have infinite number of prime numbers. So take the first prime number, 2. Now, we have already every room is being occupied. So what we are going to tell is that we are going to tell the guest in the first room to move on to the 2 raised to 1th room. Guest in the second room to move on to the 2 raised to 2th power room, that is 4th room. Guest in the third room to move on to the 2 cubed room, that is 8th room, and so on. So by this way, we can assign every guest which has been already occupied onto some powers of 2th room. Also, which also gave us enough rooms, enough vacant rooms, so that we can accommodate the guests from the next room, next best. So take the next prime number 3. From the first best, take the guest which is seated in the first seat. Assign him onto the room 3 raised to 1. Take the second guest seated onto the second seat onto the best. Assign him onto 3 square, room number 3 square, and so on. By this, continuing like this, we can assign all the guests in the first best also. Now take the next prime number, which is 5. And also take the guest who is seated in the kth seat on the second best and assign him a room number 5 raised to k. So since the prime numbers is actually infinite, we can continue this process infinitely many times. And also, for every prime or prime powers, there exists no common factors, or GCD of every prime powers, different prime powers, is actually 1. So which means that there exists no common rooms for every guest. So every guest has been occupied into different rooms. So which means that if there exist infinitely many guests coming by infinitely many bases, still we can accommodate. Or in other words, Aleph naught times Aleph naught is actually Aleph naught. So if you add infinitely many guests which is coming under infinitely many bases onto the already existing case, still the cardinality does not change. So that's the idea. So the cardinality does not, in the case of transfinite number or Aleph naught or the cardinality of natural number, which does not change even if we add a finite set, infinitely many infinite set onto that. So that's the idea. Now we have already discussed about one type of cardinality. Now the question is, does there exist any other cardinality? Or if every infinite set has the same cardinality as the set of all natural numbers? This was one of the prime important questions with regarding to this study. We have already discussed that set of all natural numbers has infinite number of elements. So now the question is, does there exist any other set which has infinite number of elements which does not have the same cardinality as the set of all natural numbers, or in other words, which does not have a bijection from the set of all natural numbers onto that set? So let's move on. We have a classic set which is called the set of all real numbers. Since open interval 0, 1, which consists of all the natural numbers in between 0, 1, is actually a subset of set of all real numbers, what we are going to do is the fact that we are going to say there exists no bijection from set of all natural numbers onto this interval, which means that the cardinality of n and the cardinality of 0, 1 is not same. Even though the cardinality is actually infinity, and set of all real numbers has a greater cardinality than the set of all numbers in between 0 and 1, which means that the set of all real numbers has a different cardinality than the set of all natural numbers. So this is what we are going to do. For that, we assume that there exists a bijection from the set of all natural numbers onto 0, 1. So every element in 0, 1 can be assigned to a natural number. So 1 is being assigned to this number, let's say. 2 is being assigned onto this number, let's say. 3 is being assigned onto this number. All of these numbers are in between 0 and 1. And so on. We can assign such a way. Now, if the set of all cardinality or the cardinality of natural numbers and cardinality of 0, 1, open interval 0, 1 is being same, which means that there exists a bijection between these two, which means that corresponding to every real number in between 0 and 1, there should exist a natural number assigning to that number. If at all we are able to find a real number which is in between 0 and 1, which is not in this collection, we got a contradiction. So what we are going to do is, we are trying to define a real number which is in between 0 and 1, which is not in this collection. So how does we do that? What we are going to do is, take the first element and take this red colored entries. That is, the first entry of the first number, the second entry of the second number, the third entry of the third number, or the fourth entry of the fourth number, fifth entry of the fifth number, sixth entry of the sixth number, and so on. We can continue like this. And change every entry. So if this is actually A1, change that A1 onto some other number. So instead of 2, we are actually giving 3, which is, let's say, B1. Instead of 5, we are giving a new number, which is actually B2. Instead of 6, we are actually giving a new number, which is B3, and so on. So thus, we can construct a new number, point B1, B2, B3, B4, etc., which could not be in this collection, because this cannot be the first number, because we have changed the first entry of the first number to form this number. This cannot be the second number, because we have changed the second entry of the second number to form this number. This cannot be the third number, because we have changed the third entry of the third number, and so on. This number is not in this collection, which is an element in 0, 1 as well. So every element in 0, 1 is not in this collection. So we cannot say that there exists a bijection from n to open interval 0, 1. So the cardinality of n and the cardinality of 0, 1 is not actually same. Since we already know that the cardinality of 0, 1 is actually infinite, which is trivial, so we must have two different classes of infinities. This is the classic result which we want to discuss, which we are actually going to discuss, and which we are actually going to understand. So there are two types of infinity. One is the infinity which is said to be the cardinality of the set of all natural numbers. The another one is the cardinality of open interval 0, 1, or the cardinality of the set of all real numbers. Both of them are infinity, and both of them cannot be actually equal. So as a mathematician or a mathematics enthusiast, What we should know about infinity is that for the mathematician's concept, we have different classes of infinity. For every others, there's only one infinity which cannot be actually defined. But in our case, infinity is actually two different classes. The first class is the cardinality of the set of all real numbers, which is called the continuum, which is denoted by C. And second is called the cardinality of the natural numbers, which is called Aleph naught. And we have already discussed its properties. Now using this, we can actually classify infinite set into two classes. If there exists a set which has the same cardinality as the set of all natural numbers, which means that there exists a bijection from n to a, we can call that set as a countably infinite set. So, every set which has the same cardinality as set of all natural numbers or the cardinality as Aleph naught is a countably infinite set. A set which has not the same cardinality as n, or it has the cardinality as the set of all real numbers, it has the cardinality as the same cardinality as the set of all real numbers, is called a set which is not countable or which is uncountable set. So using this fact, we can actually classify infinite set into two classes. One is countable, which means that we can actually count the number of elements. We can count the elements. And another one is uncountable, which means that we cannot actually count the elements on a particular order. So these are the two different classes of infinity which we are going to discuss, which we have understood. Now let's move on to the last part of the lecture. So we have discussed that there are actually two different classes of infinities or two different transfinite numbers. Now the question is, are there more transfinite numbers exist? So which can be established using this famous theorem which was proposed by Cantor, which states that there exists no surjection from a set A onto its power set. So if at all there exists a surjection from A to P of A, by previous definition, the cardinality of P of A should be less than the cardinality of A. Since there exists no surjection from set A to P of A, we can clearly say that the cardinality of the power set of A cannot be less than the cardinality of A, or the cardinality of A should be less than the cardinality of power set of A. So there exists no set which has the same number of elements as its power sets. That's the idea. Using this fact, we can have the following important aspect. The first one is the cardinality of natural numbers, which is a transfinite number, which is Aleph naught, which should be less than the cardinality of power set of n, and which should be less than the cardinality of power set of n. All of them are infinity. All of them are actually different types of infinity. So we can actually define different classes of infinity, and we can have an ordering relation between them as well using this relation. So there are actually lots of transfinite number in this case. And also we have a classic result which I am giving to you to establish. The result is that the cardinality of power set of n is actually the cardinality of real numbers, or the number of subsets of the natural numbers is same as the number of elements of the real numbers. This is a classic result. So to conclude the whole thing, we have different, not only infinity, we have different classes of infinity. And also, one infinity is actually superior to the other infinity as well. That is, if we consider cardinality of n as Aleph naught, cardinality of P of n as C, Aleph naught is actually less than C. That's the idea. Now using that, we can have a classic open problem which is called the continuum hypothesis, which states that there exists no transfinite cardinal falling strictly in between Aleph naught and C. We have already discussed that cardinality of natural numbers is less than the cardinality of power set of n. That is, Aleph naught is strictly less than C. Now the question is, does there exist a number in between Aleph naught and C? Which was a problem proposed in ICM 1900, which is called the continuum hypothesis, which is still unsolved, but two famous mathematicians, Kurt Gödel and Cohen, together implied that it is not an easy task to solve this problem. And using the existing conditions, it is really difficult to solve this problem. So it is a problem which is for you. You can actually discuss, does there exist a cardinal number in between, or does there exist a transfinite number in between Aleph naught and C? You only have to find a set whose cardinality is actually in between Aleph naught and C. That's the idea. So, which is not an easy task. So, let's summarize the whole thing. We have discussed that infinity is not actually a unique thing. We have different class of infinity with regard to the size of the set of all natural numbers and the set of all real numbers. And this concept, all of this concept, as I have discussed, has been proposed by the famous mathematician Cantor. And his quote was, the first time he proposed about this infinity, he faces a lot of backlash from the scientific community. He was considered to be a madman, and a lot of people questioned his concept. But he said that my theory stands as firm as a rock. Every arrow directed against it will return quickly to its answer, and the rest. So every doubts regarding this concept, every doubts questioned regarding this concept, thrown at this concept has been returned without much implication, because this concept was really firm. This was one of the classic concepts. This was the most easiest way to define the different classes of infinity. We have not only defined infinity, we have successfully defined different classes of infinity. That is the contribution of Cantor. Due to that contribution, he was considered to be a madman by many of his peers. So he has sacrificed a lot of things to develop this concept. So please remember him in your mathematical study. He is considered to be the father of set theory, and his contribution lies much far ahead in mathematical science than the concept of infinity. So this is regarding the concept of infinity. We have successfully defined the infinity as the sizes of the set of all natural numbers and the set of all real numbers, and which holds a relation that the cardinality of set of all natural numbers is less than the cardinality of real numbers. So thank you for giving me this wonderful opportunity. Thank you for listening to this lecture. I hope you had a wonderful time. You can refer this on Introduction to Real Analysis by Bartle and any other analysis books. So I hope you had a wonderful time. Thank you.